So for mitochondrial sorting, what I want to do is do the big picture and then do the zoom in details of it in just a second. But first of all, let's start with the big picture. And that involves the fact that we have to account for, which is that mitochondria is full of proteins, almost all of which are encoded by nuclear genes. And there is a regulatory reason why that makes sense that we don't need to worry too much about, but we do need to account for the mechanisms by which those proteins get there. And part of the complication, other than the fact that we got to start in the cytoplasm with ribosomes translating the way ribosomes do in the cytoplasm, is that we've got to get those proteins to multiple compartments within the mitochondrion. So that rather than having a process like ER sorting, in which the ribosomes start translating and then stop and then end up going down to the surface of the now rough ER, like so, and then translocating and translating at the same time and putting a protein into the lumen of the ER, like so, we're dealing with a process that begins out here in the cytoplasm and produces a full-length but only partially folded polypeptide. And that polypeptide, conceptually speaking anyway, does this. It goes from the cytoplasm to wherever it is supposed to be in the mitochondria, and we'll talk about where it's supposed to be in a minute. But for instance, it could be in the interior in the matrix, like so, but it could also be something like a respiratory chain component, which is supposed to be right about here, somewhere in the embedded in the inner mitochondrial membrane, or in the inner membrane space, or in the outer membrane. All of those things are required in order to account for all of the sorting pathways, and that's where the complexity comes from. So among the things that we've got to do, we've got to account for the processes that get the partially unfolded protein to the surface of the mitochondria, and then account for the processes that put it where it is. And as I mentioned in class, strange as it seems, the process almost always works by sending the partially unfolded protein into the matrix and then sorting some more from there. So some proteins stay here, but other proteins end up here, and some end up here, and some end up here. But the path is cytoplasm, matrix, and then the final destination in many of the pathways. So the part from cytoplasm to mitochondrion is pretty well known. The protein is maintained in a partially unfolded state and still safe from aggregation or from destroying other proteins in the cytoplasm by virtue of this association with the HSP70s that are specific for mitochondrial proteins and specific for the translocation process, or the targeting process that gets them to the outer membrane where they encounter receptors. Another thing to keep in mind is that this blue thing that I've been drawing has its own N-terminal extension that serves as the zip code for the location, in the sense that mitochondrial targeting sequence, or matrix targeting sequence, as this diagram shows you, is the thing that basically broadcasts, I am going to the mitochondria, send me there. So that's the way that signal sequence works, and somehow it communicates with particular HSP70s to accomplish that. No need for you to know how that works, because it's not, we have enough things to worry about. So what's shown on this diagram is the translocation process that does most of the sorting, the pathway that's the majority phenomenon. So a receptor binds, there's a translocon that's specific for the outer membrane called TOM, translocon of the outer membrane, that is shown open now in step 3, sending at this point, the matrix targeting sequence, and then the rest of the, still we can call it nascent chain. It was made a long time ago, but it's still partially unfolded, so we can call it nascent, I suppose. And that proceeds to step 4, in which that translocation event continues through the intermembrane space and then into a translocon of the inner membrane called TIM. The reason that process translocates is standard Brownian ratchet action of yet another HSP70 that is specifically localized to the matrix of the mitochondrion. So it's using Brownian ratchet mechanisms to pull the nascent chain into the matrix where it folds, and in some cases, in the simple pathway, produces this is a soluble matrix protein that is working and its destination is complete. But we've got to take this concept and account for other targeting pathways that would put that protein here, here, and here, or put a different protein that belongs in different regions at those locations. So this could be the respiratory chain complex. It could be TIM itself that's got to get there somehow, right? And then we also have to account for something like cytochrome C in the inner membrane space and TOM components and other outer membrane proteins in terms of that sorting pathway. So now if we, let's say, zoom in on this region of the mitochondrial outer and inner membranes for a second, then we have something that looks kind of like this. And if we zoom in on this area now, then the Brownian and ratchet type mechanism, you can imagine, is kind of pulling this thing through both of those translocons. And as that's happening, or shortly after it happens, you'll have the protease process that removes the matrix targeting sequence. And in the case of proteins whose function is to be a soluble protein in the matrix, that protein will undergo a standard folding reaction in the matrix of the mitochondria with no additional targeting sequences on it, so it just stays there. So it exists as a mitochondrial matrix protein, and it would be the equivalent of some globule thing right here. But as I mentioned, there's many other sorting possibilities, and those are required in order to make integral membrane proteins in the membranes and also proteins in the intermembrane space. And because there are additional sorting reactions required, there are additional sorting sequences. And I don't know what color to make them. Maybe I'll just make them red again. But now let's do a different color. Save it brown. That would be a sequence typically that's left at the N-terminus. So in the original diagram, it would be the sequence that comes right after the red sequence. And this would contain the zip code that specifies the further location pathway involved. So if this protein is eventually going to be an integral membrane protein, then that fact will be represented by the N-terminal sequence that comes just after the matrix targeting sequence and is essentially exposed when the matrix target sequence is removed. So now you have a pathway that would take that protein and make an integral membrane protein right here, so that the final fate of that thing would be something that might look like this. And strangely enough, there are pathways, very common pathways as it turns out, to make soluble intermembrane space proteins that would correspond to arrows that look like this, and would put a blue soluble folded protein right here. And since we've gone this far, there are pathways that would do this, create an integral membrane protein in the outer membrane, even though that protein began in the cytoplasm, went through and all the way into the matrix, and then is sorted back to the outer membrane. And those are the most common localization pathways, even though they are definitely counterintuitive. And part of the reason why it makes sense, even though it's counterintuitive, is this idea that the mitochondrion was once a bacterium. So there is a genome in there that is making some protein through transcription translation mechanisms. So there is a sorting pathway that handles those genes, and it can be piggybacked in the case of the nuclear-encoded genes that come in through TIM and TOM. And overall, that process makes sense, again, from a regulatory standpoint. Just to make matters a little bit more complicated, it's also observed that integral membrane proteins in the outer membrane sometimes get there through the function of something similar to a stop transfer sequence in the nascent chain. So in this case, there would probably be no matrix targeting sequence on this protein, but instead what would happen is a pause in the translocation through TOM, and then the lateral movement of that thing to make an integral membrane protein in the outer membrane. And then likewise, you could do exactly the same thing, only make the nascent chain migrate all the way into TIM and have a stop transfer sequence that operates through TIM. And you might imagine that process is looking like stop transfer hits, moves this way into the membrane, like so, and that produces a integral membrane protein of the sort like the respiratory chain in the inner membrane of the mitochondria. So the overall locations in this diagram would be matrix, inner membrane space, and outer membrane. All of those pathways exist, and they are required in order to make the entire complement of proteins in the mitochondria, including the ones that are nuclear-encoded and mitochondrially encoded.